Good morning, I'm Marco Zordan and today I'm going to present a work about numerical model for the analysis of shear wall in light steel residential steel building. We start from a brief introduction about the system that you're talking about, which are light residential steel building made of conformal steel members. But why this solution and which are the advantages? This solution have high structural performance given by the high ratio stiffness way. They can be quickly built because of the modular and dry construction technique. And finally, they are light, which make this structure suitable in seismic zone. From a structural point of view, they can be seen as a system composed by shear wall and floor interacting between them in the mechanism of the fault transfer. For this reason, their characterization is needed for the right assessment of the building performance. In particular, in this presentation, we focus on the shear wall system. In detail, we investigate the shear behavior of the wall, that is one of the main parameters that rule the seismic performance of the wall system, since they provide the bracing system of the wall structure. But the complexity of this system, combined with a limited knowledge, stresses the use of the so-called design assisted by testing approach that allow us to determine the parameters that rule the lateral response of the wall. In addition, numerical simulations are needed as well to preserve the cost and extend the cases of the study. Therefore, they need a proper validation against the experimental results. I report here the main data of the experimental program. In detail, 21 specimens of 16 different configurations were tested, with the aim to characterize their in-plane behavior. The configuration differs from the type of steel frame, the member depth, the presence of the down, the presence of the sheeting, and eventually the type of sheeting. As you can see, several bracing systems were taken into account, ranging from the classic solution with diagonal strap to the new trussed solution that may host opening like windows and doors. Both monotonic and cyclic protocols were applied to the walls. Here you can observe the main result of the experimental test. In detail, the presence of the down significantly increased the performance of the wall. The presence of the opening doesn't affect the performance of the wall. As expected, the diagonal strap solution showed the best performance, and eventually, the sheeting increased the strength and the stiffness of the wall with a response mainly ruled by the sheeting to frame connection. As to the cyclic test, the responses show a remarkable pinch effect as highlighted in the figure below. Among all these configurations that we have seen, I selected 3 of them on which develop and calibrate the numerical model. In detail, the first, G9XX, is a bare frame configuration featured with a diagonal bracing systems. The second, G9JH, has the same steel frame of the first, but is completed with the sheeting. The third, G8AF, is another sheeted solution, but it has no bracing system and used panel with different materials. In addition, the panel of the sheeted solution are attached to the frame by means of self-drilling screw. All these configurations are analyzed through a monotonic and cyclic procedure in accordance with the experimental test. The analyses were performed through a static procedure taking into account the geometrical and material non-linearities. We created 2D and 3D models using the OpenSea software, as well as I used Abacus for component characterization, such as the member response. Here you can see a schematic view of the model with the elements that are included. In detail, the steel frame is modeled with beam column element and truss element, while the sheeting is modeled as a rigid diaphragm connected to the steel frame by means of spring elements simulating the sheeting-to-frame connection that in turn are characterized by a pinching behavior. Now we move to see in detail how the single components were characterized, starting from the steel frame. The diagonal straps that are only in the G9 configurations were modeled through a truss element, forcing the compression behavior to not exceed strength. In this way, the effect of the buckling in the diagonal straps was simulated. The up-down were simulated through spring elements named zero-length element in OpenSys, and their tension behavior was characterized through experimental tests. The members were modeled through beam column elements, characterized by an axial and bending behavior that take into account the effective stiffness and the post-buckling effect. In order to achieve this, we perform abacus simulation taking into account all parameters that rule the behavior of the member, which are the type of action, the length of the profile, the material, and the imperfections. From the simulation, we hence obtained the force displacement and moment rotation curves used to define the rheological model of behavior to assign to the beam column elements. About the action, we consider the axial force and the bending moments. These were applied to the member length equal to the unbraced length between the sheeting-to-member connection and between the member-to-member connections. This allows us to consider the different buckling modes that can occur on this element depending on their length. As to the material, this was characterized by a hardening and damage calibrated on experimental tests performed on several material components. Finally, the imperfections were simulated through a monodimensional spectral approach capable to generate a random imperfection field at every analysis. In this way, the random nature of this phenomena was sketched. As to the sheeting, it was modeled by means of two solutions. The first adopts elastic shell element with a modulus of elasticity according to the material specification, while the second adopts rigid constraints in order to simulate the panel as a rigid diaphragm. In this way, we can investigate how the flexibility of the panels influences the lateral response of the wall, comparing the results of these two solutions. The in-plane behavior of the sheeting-to-member connection were modeled through zero-length elements assigned the pinching flow model. This model enabled the simulation of a cyclic behavior that exhibits damage and pinching phenomena. The connection distribution is based on the actual arrangement of the fastener for a total of 174 zero-length elements. Here you can see the result of the simulation. As you can see, they are in agreement with experimental tests, both in terms of force displacement curve and energy dissipation. In addition, no differences in the response were observed for the model with shell element and the model that simulated the sheeting as a rigid diaphragm. This pointed out that the response of the sheeting solution is mainly ruled by the sheeting-to-member connections. In particular, in this slide, I reported the distribution of the connection reaction within the panel. As you can see, they are concentrated in a panel corner and the mid-seams between the two panels. This is also demonstrated by the damage grade reported in this figure, since the damage was included into the connection model. In conclusion, we have seen that the simulations are in a good agreement with the experimental test, but these results have required a proper characterization of the single component, taking into account all sources of nonlinearities. Finally, we have seen that the sheeting configurations are mainly ruled by the behavior of the connection rather than the property of the sheeting itself. Thanks for your attention.